So hello everyone, my name is Alexis Tyndall. I'm the Manager of Digital Innovation here at the University of Adelaide Library, if you haven't met me previously. So just before we start, I live and work on the lands of the Kaurna people, and before we start I'd like to acknowledge and pay my respects to them as the traditional custodians whose ancestral lands we gather virtually on today. I acknowledge the deep feelings of attachment and relationship with the Kaurna people to country, and respect and value their past, present and ongoing connection to the land and cultural beliefs. At least one of our speakers, Jonathan here, is joining us from Sydney on the lands of the Gadigal people, and there may be people beaming in from elsewhere online, so I extend that respect to the communities that are represented from other regions and any Aboriginal and Torres Strait Islander people who are joining us here today. So welcome to the third webinar in the 2021 series of the University Library's Digital Humanities Lab program. Welcome back to those of you who've joined us before, and hello to our new faces. The objective of this series of webinars and in-person events is to showcase digitally innovative work that the University of Adelaide, from our researchers and our community, and to encourage and inspire researchers or students who are interested in using digital methods and tools, make them aware of some of the resources in this environment that are available to them, support a bit of peer learning where we can, and facilitate networking that may in the future lead to interdisciplinary collaboration. We will have another webinar before the end of the year and another in-person event. As you have registered for today's webinar, I will add you to my circulation list for future digital humanities events, so please feel free to opt out at any time. Today, we're talking about a digital method that's increasingly used in the humanities and other fields, network analysis. This approach is offering researchers new perspectives on source material, whether that be historical records, text, creative work, social media, or even, as we're here today, particles in the Large Hadron Collider. Network analysis can uncover patterns or relationships that will prompt new research questions, and it can create and share visualizations that help share our research outcomes or encourage collaboration between researchers. So before we start, just a little bit of housekeeping. Today's session will be recorded and shared after the event on the University of Adelaide YouTube page. If you have any questions, just look at the bottom of your screen and you should be able to see a chat icon. Ask your questions in that chat window. We will have the presentations, the three presentations, one after the other. Feel free to ask your questions at any time, and at the conclusion of those presentations, I'll pose those questions to all of our speakers, and hopefully have a little bit of time for a good discussion. So yeah. So we'll kick off. First up, we've got Gareth Pritchard. He's from the University of Adelaide School of Humanities. He's a historian of 20th century Europe with a particular interest in the social and political history of the 1940s and the enduring legacy of the 1940s in post-war contemporary Europe. He's interested in the history of protest and revolution, and has published and contributed to a number of books on the history of Germany, especially considering the social, political and activist movements of the 1940s. He is also a very well-loved teacher who gets very good reviews from his students. So I'm looking forward to hearing from him today. And with that, I'll let Gareth kick off.
Thank you very much. So I'll just share screens, hopefully. Have I successfully shared screens? Yep, good. So I'm mainly interested in social network analysis as a teaching tool. I am beginning to use it in my research, but it's mainly in the classroom that I've deployed it. What I'm going to do today is just talk about a couple of examples of SNA, social network analysis in practice, that I think are really cool. And then I'll talk about what I do. So the first example I want to talk about is a large-scale study by Ilka Heemskeert and colleagues, and they're interested in the structure of global capitalist elites. And what they did was look at data from 5 million companies across the world, in particular in terms of who sits on the boards of directors. And above all, they're interested in people who sit on more than one board of directors. What I found very interesting about this study is that they didn't impose any a priori categories on the data, such as the nation state. They let the structure itself drive the categories that emerged from the study. And what they discovered was that the world is divided into about 15 global clusters in terms of the directors of companies. And in some cases, these clusters coincide with an individual country. For example, the Russian cluster is more or less coterminous with the Russian state. But there are also many clusters that are transnational. So if you look at the bottom right-hand corner of the screen, you'll see that Australia forms a cluster with New Zealand, Malaysia, India, and South Korea. There are also some countries that contain more than one cluster. So in the United States of America, there are in fact 3 clusters, one on the East Coast, which looks towards Europe and the Atlantic world and incorporates Israel, one on the West Coast, which looks to the Pacific, and one in the center, which is more or less contained within the borders of the United States. Now, these clusters can't be seen except through the use of social network analysis. And this is why I think it's so exciting. We're all embedded in structures. Every day of our lives, we're embedded in all kinds of structures. And these structures affect the way that we behave. They affect the way that organizations work. They affect the way the economy works. They affect the way that ideas spread. They affect the way that pandemics spread. But the structures of these networks are fantastically complicated. And it is only really with the help of digital technologies that we're able to unpack them. So the second study is a much smaller scale study by Jennifer Neal. So the first study is what most people think of as social network analysis. It's big data, lots and lots of data. This is a much smaller, more modest study, but nonetheless very interesting. And what Jennifer Neal did was look at 2 classrooms in a Northwestern school in the United States, 56 adolescents in all. And what she did was simply to ask the students to identify which of the other students they socialized with. And she discovered then that the 2 classes that she looked at were actually structured very differently. She used the Gini coefficient to measure to the degree to which the social network was centralized or decentralized. And you can see in the 2 graphs there that the 7th grade classroom was actually clustered towards the middle in terms of the Gini coefficient, which means that no students were exceptionally popular and no students were exceptionally unpopular. In the second class, however, the 8th grade class, the Gini coefficient was much more spread out, which means that you had some very popular students, 2 in particular, and other students who didn't have any social connections with the class at all. And what I found so interesting about this is that these differences in the structure of the classroom actually impacted on the behavior of the students. So in the 8th grade class, the more centralized class, the more hierarchical class, there was more bullying, more gossip, and worse learning outcomes. And again, these are structures that wouldn't be immediately apparent. They only emerge with mathematical analysis, and yet they're really important to the way that students behave. So what I'm interested in doing is trying to apply these techniques to the classroom and to get undergraduate students involved in a social network analysis project. And I'll give you an example of how I've been trying to do that in a moment. So there are many advantages, I think, to using SNA as a pedagogical tool and not just as a research tool. Using social network analysis, it's possible to turn a course, into a genuinely collaborative research project in which the students become co-creators and partners. The basic mechanism for doing this is to divide the collection of data between the students, whether they are working in teams or as individuals or both. The role of the teacher in this kind of project is not to convey information, is not to be the all-knowing guru at the front of the class, but rather to coordinate the activities of the class as a whole, and also to help students make sense of the information that they have discovered for themselves. An SNA approach also is fundamentally interdisciplinary, and it creates opportunities for all kinds of interesting things that take us beyond narrow disciplinary confines. So in my work, for example, with students of history, we use a lot of statistics. And some quite sophisticated statistics. And this is not something that history students would normally encounter. Another advantage of SNA in the context of the classroom is that it can help to democratize the learning process. Students now become co-creators. They are colleagues in a collective enterprise. And this can only really work if the students are involved in the course design and in the actual day-to-day running of the course. So in my experience, these kinds of courses have a very different dynamic to that of a more traditional course. And there's a genuine sense of discovery. At the outset of the course, I don't know what the students are going to discover. I have no idea what it's going to produce. And often I find the results quite surprising. And the kinds of things we're discovering are facts about these social networks, which have been buried in the statistics, but nobody's ever seen before. So that the work we're doing is genuinely cutting edge with the students. We're making discoveries that they will not find in any textbook, in any academic monograph. This is new terrain. So this is the course in which I make most use of social network analysis. It's a course called Russia in War and Revolution. It's a course about social networks of political, cultural, military elites in the years just before and just after the Russian Revolution of 1917. It started life as a very traditional course, very similar to the kind of course that I took when I was an undergraduate, but it's morphed over the years into something that I think is much more exciting. So the way that it works is that every student is assigned an historical individual to research, whether that be Gorky, Maxim Gorky, the writer, Lenin, Stalin, Rasputin, Nicholas II, Alexandra. There are about 600-700 individuals in all in the pool of historical characters that are available to study. And what we're particularly interested in is who's hanging out with whom, who has a relationship with whom. The students compile information on their assigned characters and they enter that data into a custom-made database. I then download the results using Gephi software and turn it into a social network map such as the one you can see on the screen. Now, what this map does is reveal the position of individuals relative to the overall social network in Russia at the time of the revolution, but also the position of individuals relative to the cluster of individuals within which they're located. So these red colored individuals down here, they're the Bolsheviks. Blue is the old regime, green are artists, cultural type people, and so on. The closer somebody is to the center of the map, the more important they are, the more connected they are. So Maxim Gorky, for example, the writer, is absolutely right at the center of the network because he's talking to everybody. He's talking to the Bolsheviks, to the artists, and even to people from the old regime. But you can also see where people fall relative to their own cluster. So if you look at the big huddle of Bolsheviks, you'll find some Bolsheviks are on the edge of that cluster because they're talking to people who aren't Bolsheviks. But right in the middle, you've got Bolsheviks who aren't really talking to anybody except Bolsheviks. Now, I don't have time to go into why this is so significant, but believe me, it really does matter. Now, I've come across a number of problems in trying to adapt social network analysis in the classroom. One problem in this course is the unevenness of the data. So for some characters like Maxim Gorky or Lenin, there's lots and lots of data. For other less well-known characters, there is much less. Another big problem is that sometimes students supply unreliable data, and that gets into the database and it rather corrupts the data pool. What I'm going to do there's a typographical error there. What I'm going to do in 2022 is actually try and get around the first problem by expanding the geographic scope, but contracting the chronological scope. So we're just going to look at a single year, 1913, but right across the whole of Europe. So we're going to have Einstein in there, and Sigmund Freud, and Virginia Woolf, and D.H. Lawrence, and so on. Picasso is going to be in there. All of these are famous people. There won't be any problem in gathering the data. The other thing that I'm going to try and do is to render this in a 3D format so students can explore the network on their computer screen, and also, if possible, to try and render the social network in a virtual reality environment. Okay, so that's all I have to say.
That's great. Thank you very much. I think I want to sign up for that 2022 class. It sounds like an interesting exercise. I just quickly we'll hand over to our next speaker, Jonathan Bollen, who is joining us from Theatre and Performance Studies at University of New South Wales, Sydney. Jonathan researches performance, mobility and desire, and recent projects have studied the regional development of international touring, entrepreneurial diplomacy and commercial entertainment by mapping touring circuits that stretch across Asia and the Pacific in the 1950s and 60s. He's written several books on variety and performance, and has published on data models for theatre research, and contributed to AusStage, which some of you will be familiar with, Ibsen Stage and the Philippine Performance Archive. And with that, I will hand over to Jonathan. Thank you.
Thanks, Alexis, and thanks for kicking us off, Gareth. I'm going to share my screen and hit play. Also like to say thanks to Jenny Fuster and my colleagues at AusStage, the collaborative online resource and database for Australian live performance. Today, I'm going to describe an approach from theatre studies and performance history to visualising networks of people, places and events. And we're going to start with some concepts, which I'll introduce in a schematic way, and I'll then share some examples from my research. So here's an event, you know, taking place somewhere, sometime. It appears, it happens, then it's over, it's gone. And what makes an event happen are the people it attracts, the creative team, cast and crew, the artists who are drawn into the production working together for the duration of an event. In turn, the creative activity of the artists collaborating on the production attracts an audience as well. So we have artists collaborating and audience attending. The kind of attractive hub of creative activity intensifies for a period and then disperses. And we can think about these things happening, you know, flashing on and off, as we've just seen. And sometimes they all happen at once. That's like a festival. But what if we're interested in following the relations between events? What we can do in that case is follow one artist, as I'm showing here, follow a person moving from one event to the next event. People are mobile. They can go to a sequence of events in time. They're attracted to a venue for the duration and then released to move on to the next event. And if we take a set of events like this and follow the movements of people over a given area through a duration of time, we can start to see patterns of convergence, dispersal, reconvergence in different combinations as artists come together to work on events. And what we're tracking here, and this is the kind of basic image that I want to share with you today, is a dynamic network that unfolds over time as artists move from production to production, forming a network of artistic collaboration over time and space. So here are the three concepts that I'm going to take into, that we've been working with and will take into the research. The first idea is the idea of an event where people come together in a place for a time. The second idea is to think about people as linking a series of events over time, a trajectory or a career, if you like, of what an artist has done. And the third idea is the network of who is working with whom on what, where, and when. So they're the ideas that we've been working with on network analysis and artistic practice in theatre studies and performance history. And I'm now going to talk through 3 examples from my research where we've put these ideas to practice. The first example focuses on the Broken Hill Repertory Society, an amateur theatre company founded in 1946. And I worked with Murray Couch, building a data set in Ausstage of their productions from 1946 to 1969. And having compiled that data set of who works with who, we're able to form a timeline here of the producers, the directors of the productions. And one of the things we were interested in was the role of women as producers in the gender order of Broken Hill, and the scope for productive capacity and creativity that the Repertory Society offered a large group of women. A timeline gives you a very schematic view, but when we did the network visualization of who's been working with who on productions, this is what we found. I've highlighted the women in black here, and this visualization shows each of the productions in a temporal sequence that's colored from red at the top here through unfolding over time from 46 through to 69 in this data set. And we were very interested to see the women as providing a kind of a backbone through the flow of productions. The other things you can see here is that it's like a kind of sausage, that productions that are near each other in time draw on the same people, yeah. But every now and then there are productions in the middle period here that have had to draw someone from the past production to come in. And if you know anything about amateur theatre, you'll know that men are always in short supply. And so some of these links that are producing the S-bend are men from, you know, productions in the 1940s that were brought back to play a role in a production in the mid-60s. So it became a way to think about the social relations and the gender order of the Broken Hill Repertory Society in the context of Broken Hill. Next example comes from collaborative work on Ibsen's A Doll's House. Henrik Ibsen, the world's second most produced playwright, and A Doll's House is Ibsen's most produced play. On this project, which I undertook with Julie Holledge, Frode Helland from the University of Oslo, and Joanne Tompkins at UQ, we were focused on writing a global history of A Doll's House from 1879 to the present, working with records of about 5,000 productions that had been collated at the University of Oslo. One of the fascinating things about working on a canonical play that's had many productions, thousands of productions over time, is this question of the persistence of the performance imagery and the performance, the embodiment of the performance that we can see here in this series of photos from Betty Hennings in the premiere production 1879, Dancing the Tarantella, through to Miranda Otto at the Sydney Theatre Company in 2002. This kind of phenomenon raises questions about the transmission of the play script, but not just the play script, the transmission of the performance as an aesthetic and a kinesthetic embodied form. In this work, we we're interested in looking globally at the production history. And here on the left-hand side, we've produced a time map where you can see the main kind of time going up the page, and the main trunk of activity is focused on Oslo and in the Nordic region, but there are various kind of tours, a very early tour that reached Sydney and Auckland, and other tours, and then an explosion of international activity in the last 2 decades. We were particularly interested in one chapter in focusing in on this backbone, and that's what the second visualization here displays. This is also time going up the page from the Copenhagen 1879 premiere production, following artist-to-artist connections through an unbroken series of productions from 1879 to 1990. We were able to follow that. So here's what this looks like running up the page. That's Copenhagen at the bottom there, and we're trucking through productions. There were these long tours, and eventually we get to 1990 at the end there. This provided us with a backbone not only for analysing the set of tambourine tarantella photographs, but other details that may not have been observed about the transmission of performance knowledge through this line, like this image of Helmer responding to Nora dancing the tarantella from 1879 to 1990. Remarkable consistency of imagery, and we now have the line of connection to understand how the bodily knowledge of this performance was transmitted between these two actors almost, a century apart. Similar story to the series of Christmas tree images from 1936 also through to 1990. So we've used network analysis here to investigate the cultural transmission of embodied performance knowledge between artists in rehearsal room over really long stretches of time. And my third example comes from my most recent research, a book on touring variety in the Asia-Pacific region. So really different kind of performance to be writing about, but similar techniques of analysis. In this project, I was interested in following the artists touring the circuits of variety theatres and commercial nightclubs in the Asia-Pacific region, including Australia, Sydney, Brisbane, Melbourne, Manila, Singapore, Hong Kong, Taipei, Tokyo were the main hubs of the network in that period of time. I worked from classified advertisements in newspapers in each site. So here's a set of advertisements from the newspapers in Hong Kong. From those advertisements, I extracted basic performance information about the place, the venue, the date, the companies and the people. And for Hong Kong, over 10 years from 56 to 65, I compiled a data set of almost 5,000 performances, appearances at 61 nightclubs and other venues, about 1,000 companies appearing in that, companies and artists appearing in that time. And working with that data set, I was able to produce a series of analyses, visualizations to help me answer these questions about who is working with whom in the nightclubs of Hong Kong. With thousands of people, there are many opportunities for encounters in those years. Acts were advertised by their origin or nationality. So I was really interested in tracking where artists were coming from and what kind of international encounters were possible in the nightclubs. And I was also able to observe just how closely interconnected these artists were. Some 85% of artists were connected with each other. That means they performed together on the same night in nightclubs. So I'll just talk, here's the kind of the main visualization of that, showing that main cluster of interconnected artists. That's a zoomed in view. So each artist or company is named and the people they've worked with are linked to. We can pick out one artist. This is the Dalrays highlighted there. They were a acro comedy duo from Adelaide who toured internationally for almost a decade. The Dalrays worked with a range of artists. So I've highlighted the artists in the network that the Dalrays worked with there. And you start to get a sense of being able to analyse who worked with who. I was particularly interested in understanding where artists came from, and what I found, this is a subset focused on one nightclub, was that I could look at the network of artists who performed at the Paramount nightclub within a defined period. The Dalrays are in this mix, But if I rearranged the network according to where artists come from, what I got was a kind of image, a map of the world, if you like, that was being performed on the, in the floor shows at that nightclub, a world of international encounters between artists from the Americas that are over there on the right, artists from Asia and Australia and New Zealand, which are the central cluster here, and artists coming in from various countries in Europe, which is the cluster over to the right. And that's Gladys Kalani there from Hawaii in the middle. So I was able to do this kind of analysis to the full data set where I had information about where artists came from. And when I did that, I got a very similar kind of world map. This is teased apart a little more. You can see the Americas, Central America, South America. This is Australia, New Zealand. There's Hawaii again. This is the Philippines and Hong Kong, Japan, Korea, Indian subcontinent, and then over the countries of Europe with some Middle Eastern artists coming in as well. Abstracting that to get this image, an image of the international relations as they played out in the nightclubs of Hong Kong. And this image, this image we can render visually like this, and it connects to a sense of the airline networks. Looks like one of those maps that you see in the flight magazine. And of course, all of this international encounters in Hong Kong were being driven by the development of commercial aviation and international tourism. It was a real hub, as we can see there. We can render this textually. So this is what the data looks like as text, 296 international combinations of varying weights. But it's much more interesting, I think, to visualize this, to imagine the variety of artists and the diversity in regional formation, particular, that was converging. And this kind of analysis enabled me to develop arguments about the significance of national origin for artists who are touring, about the way international relations were transacted in commercial entertainment within acts between artists encountering each other on tour, and also the emergence of multinational repertoire, where international touring became embodied by individual artists as a multinational repertoire that they could perform to an audience of tourists. And my best example here is this album recorded in 1974 by Frances Yip, a promotional album for Cathay Pacific, in which she sang a song, one song from each of the destinations in the airline's network. And this kind of exercise in multinational repertoire international relations could only have been produced in Hong Kong after all of that touring had and all of that diversity had accumulated over the years in the nightclubs there. So that's what I've been doing, and also work with colleagues in theatre and performance studies using network and analysis to visualize our data and to integrate it with our qualitative historical accounts. There are some publications, and happy to take questions about the software and the visualization approach. Thank you.
Yeah, that's great, Jonathan. That's an extraordinary amount of information captured in those data sets as well, and so many different research avenues that you can see emerging in those things. So that's fantastic. Thank you very much for that. Our final speaker for today is Martin White, who's from our School of Physical Sciences here at the University of Adelaide. Martin is a particle astrophysicist who uses searches in astrophysics and particle physics experiments to find and test new theories of what the universe is made of and how it came to be. He co-leads a team of approximately 70 international particle and astrophysicists who perform detailed statistical fits of new physics models. This includes new models of dark matter and will soon include cosmological models and models that explain neutrino masses. He's recently developed novel network analysis techniques for discovering new particles at the Large Hadron Collider. And with that, I will pass over to Martin. Thank you.
Okay, thanks, Alexis, and thanks to the other two speakers for very interesting talks. So I've recently pioneered the use of network analysis for discovering particles at the Hadron Collider, and this doesn't sound immediately useful to the humanities, but I'll explain why I think it is, and also something about the science itself, because I just think it's interesting. But crucially, the specific methods that we use, I can see having lots of potential uses in humanities problems. And so I'll try and give you a sense of what they are. And of course, you're welcome to follow up with me. So I'm hoping that many of you have at least heard of the Large Hadron Collider, even if you're not familiar with the ins and outs of particle astrophysics. So this is simply our biggest particle accelerator that we have at the moment. It's obviously the latest in a long line of accelerators. The next large facilities are likely to be in China and Japan. And CERN sort of keeps a presence in parallel with those other efforts. So it's 100 meters underground. That's to shield it from the sort of various particles that are flying through you at the moment on the surface of the Earth. And obviously, we want to pick up things from our proton collisions and not from the atmosphere, for example. And what we do is we accelerate protons to nearly the speed of light in 2 directions, and then we smack them together. And there's a reason to do this. Which is sort of like this. I mean, there's 2 ways to view it. I mean, one of them is that you'll be aware that the universe is basically a giant Lego set. I mean, in school, you learn about the periodic table of chemistry and the different atoms that make up all the matter that we know about. And what particle physics is it's the study of really the most fundamental building blocks. So what makes up the atom? So partly we're studying what the universe is constructed of on its smallest scales. And I'll show you that in a moment. The other reason to do it is essentially history. So the history that we've sort of already had presented to us today is mostly concerned with life, which is roughly 13.8 billion years after the Big Bang, right? And not much further back than that. What we do with the LHC is we get back to 10 to the minus 10 seconds after the Big Bang, and we're creating the kind of states of energy that existed very, very, very early in the universe's life. You'll know that the universe started very small, and then it blew up very quickly. In fact, we call that inflation. And then it expanded more slowly. But we're really sort of understanding where the universe came from and what makes it tick. So, I often describe particle physics as this humanities of the sciences. It's the thing that we do because we lay awake as kids at night thinking about where the universe came from and how it was born and what was happening in the very early days. And it's almost philosophy. At that end. Now, of course, the technology we use is useful, so we can turn up to meetings and write in grants that we're doing useful sort of transferable things. But that's not why we do it. We do it because there's a fascinating story there about where we came from. So what we found in decades of doing this kind of work is these are the building blocks of all of the matter in the universe. So on the left of this white line, you're seeing the matter. And you're mostly, in fact, made up of electrons, up and down quarks. That's most of your atoms. And then there are heavier versions of all of these particles for a reason that no one knows. We're still investigating. Then there are kind of glue particles that represent the forces that glue things together. So the strongest force in nature is the force which actually binds your protons together. And we just called the particles gluons. That was obviously a fairly lazy day in the office. The photon is the particle that represents electromagnetism, which is the same thing as light, funnily enough. And then there's this other force called the weak force, which I won't go into. Now, there's one last piece of this puzzle, which became famous a few years ago. If you write down the theory of particle physics, it's staggeringly precise, and it's incredibly accurate when we calculate things. But you can't give the particles mass intrinsically. It turns out that mass for these particles can't be an intrinsic property, and the details are highly technical, so I won't go through them. So the idea arose that maybe particles have to interact with something else to get their mass. And the simplest way to do that, which is not very simple at all, is called the Higgs mechanism. And this is what Peter Higgs dreamt up with a few other people like Englert and Brout and so on. And lo and behold, in 2012, after 50 years of searching, we finally discovered this strange Higgs boson, which is the thing which gives things mass. I was certainly in the camp that wanted something more exciting than this and not the thing that had been predicted. But it's still a very, very puzzling discovery to me. The fact that this very weird mechanism borrowed from solid state physics actually works in the universe to give things mass is itself sort of baffling, and it's still very poorly understood. We have no idea where this mechanism comes from, and that's one of the frontiers in our field going forward. Now, this sort of standard theory, we have the mathematical description of this. It's very beautiful and elegant, but it can't be the final answer. And I'll only give you one piece of evidence for that to be the case. If I look at what's in the universe as a whole, it turns out that I can learn this by studying the cosmic microwave background. So there are microwaves that are reaching us from every direction in the universe, and they're almost exactly the same temperature until I zoom in 10,000 times. And that's what I've done on the right here. And you can start to see these little wobbles in the temperature. And what this picture is, this should be much more famous than it is. It's basically the 12-week scan of the universe. You know, when you have a kid, you have a scan and you can see the seeds of the future person forming. And what we're seeing here is the same thing. Each of these bright spots is a slightly overdense region where matter's going to start piling in and kicking off star formation, and that's going to lead to the first galaxies and so on. And if we go back to here, you can see that this happens about, so actually it's the 30,000 year scan of the universe, right? It was formed about 30,000 years ago when we first formed atoms in the universe. But we have a theory of astrophysics that we can sort of compare to this data, and it tells us what type of stuff is in the universe. And the humbling thing is that the atomic matter, the matter that we learn about in school and everything you care about in the humanities pretty much, is about 4% of the contents of the universe. The dark matter there's some weird form of dark matter, which is about 23% of the universe. So it's 5 times more abundant. And then there's an even weirder thing called dark energy, which is blowing the universe outwards like an explosion. So we realized at the dawn of this century, pretty much, that's when these measurements were first made, that we really understand very, very little of the contents of the universe. And that's opened up whole new frontiers and vistas in astronomy and astrophysics. So clearly the next job for the Hadron Collider is to uncover direct evidence of the particles that might explain this stuff. There is no particle that we've ever discovered that can explain dark matter. So there's something new there to discover. We have a center of excellence here, which is doing exactly that at the moment. And the main thing to note is that despite 10 years of searching at the LHC, we haven't uncovered any evidence for any particles except those of the standard model. And so most of my work in the past few years has been trying to see, well, is this because, you know, things can't be discovered at the LHC, or are we doing something wrong? And the evidence is clear that we're doing something wrong. So this international team that Alexis mentioned, we've shown that some of the most obvious ideas for what's beyond the standard model would have been missed by all of our current searches. I can explain why if you're really interested. But the evidence is very clear. So I've been trying to develop new methods for discovering particles at the Hadron Collider. So I think I have a few minutes left to sort of walk you through particle physics in about 2 slides. This is all based on an article I wrote for Cosmos a couple of months ago, which I can share if you're interested in PDF form, because I wrote this with my master student, Anna, and it explains things at quite a nice level. But one of the big ideas for what replaces the standard model is something called supersymmetry. Basically, this would predict that there are twice as many particles in nature than we have observed to date. It gives you a dark matter candidate very naturally. And there's a whole bunch of technical issues in the standard model, which this thing solves immediately. And it's also the last symmetry that could possibly exist in nature that we haven't seen. So there's a kind of completist tendency that would suggest it was there. And the take-home message is, if it's there, there's a whole bunch of new particles that we have to find. And the job of the Hadron Collider is to uncover evidence for them. So perhaps I'll skip to this paper. This is the paper that applied the network analysis to this problem. It's called Does Susie Have Friends? And I'll explain that in a moment. And this was with my master student, Anna Mullin, and former colleagues at the University of Cambridge. And Anna indeed is going to Cambridge to do her PhD if she can leave the country later this month. And we hope to keep working on this as she progresses in her studies. So what happens when I smack protons together is something like this. The thing with quantum mechanics, which is famous and philosophers ran in all sorts of wrong directions with it, is it's statistical rather than deterministic. So every time I smack my protons together, something random happens. It's literally like rolling a dice, or rolling a die rather. And you know, I can, after a million collisions, tell you how many are going to be a particular thing. but I can't tell you the outcome of any one collision. So most of the time I smack my protons together, they make particles of the standard model, which are fairly boring. And some of the time, if supersymmetry is true, they would make supersymmetric particles, and those particles decay. So what you're seeing here is protons come together, you get these particles coming out, they decay, and we see the decay products, and we measure their energy and momentum. That's our full toolkit of how we can discover things at the LHC. But this thing would happen about 10 billion times less often than the normal standard model particles being produced. So we have to kind of sift this massive, sort of 10 billion barns of hay to find a needle hidden somewhere in there. It's a very tricky thing. And by measuring the energy and momentum of these things, those are the keys that we have to try and find evidence for something weird. So the idea of the network analysis was to say, okay, I'm going to pretend that each of the proton collision events joins some kind of particle Facebook. And if the events grew up close in energy and momentum to some other event, then I make them friends in the network. And if they are far away in energy and momentum, I don't make them friends. And what I'm doing is I'm defining something called the adjacency matrix of the network. If I take a simple network of people, here I've got Anne and Bob being connected to each other and Anne and Carol being connected, but not Bob and Carol. I can represent that as a matrix in which I stick a 1 if there's a connection and a 0 if there isn't a connection. And all I'm doing for my Hadron Collider events is exactly the same thing. I'm taking each of the events, I'm measuring their energy and momentum. And if those are fairly similar, and there's a box of maths tricks in there, but if they're fairly similar, then I can draw a connection in the network. And if they're not similar, I can't. And this is the first time anyone has looked at connections between LHC events rather than just looking at the properties of the events themselves. So then what I do is I tune the linking length, because I can choose how close they have to be to make them friends. That's called a linking length. And I can tune that so that all the standard model events are mostly connected to each other, but the supersymmetry events aren't. And so I've deliberately made it so that Susie has no friends. And the first reason to do that is to get a pun in the paper title. But the second reason to do it is because I can now look at the properties of events in the network, and their typical pattern of connections will discriminate between events which are standard and events which come from supersymmetry. And the second kind are the ones I want to isolate because there's a Nobel Prize in there, right? So it turns out this actually works. There are sufficient differences in the energy and momentum of these types of event that allows you to see differences in a network. So here you can see some examples of simulations of these Hadron Collider events, and you can see the connections that you get in these networks. They're very dense. Even by eye here, in the right, for example, you can see that the sort of pink dots are the standard model events, and they form these very closely connected structures. And then you have a sort of series of SUSY events that are less well connected. And they're mixed up a bit, but it's a fairly clean separation. So we have to build networks with sort of hundreds of thousands to millions of events in. So we had to do lots of processing of big network data. It also means that visualizing the network by hand or by eye is not particularly useful to you. So what we do is we calculate things called local network metrics. So imagine you have a network. The number of friends you have in a network is an example of something that would apply to every person in a network, and it's a different number for each person. And I could then look at the distribution of that number over all of the people. And here we're seeing a series of distributions over all of the Hadron Collider events for SUSY events and for standard model events. And I'm just showing you some examples of numbers here, which are clearly different for the different types of event. And therefore I can use these to kind of discriminate between the standard model and SUSY. And I can sort of really get evidence that I'm seeing supersymmetry. And what we proved in the paper is that for things we want to discover that we would have missed so far, this approach actually works in pulling them out of the data and allowing us to make a Nobel Prize winning discovery. So our next step is to actually do this on the real data from the Hadron Collider. And when Anna said she wanted to study abroad, I sort of encouraged her to go to Cambridge so we could keep working within the same team. So the thing that I think is useful for the humanities is the kind of technical stuff that we had to develop for this. So it turns out, I won't go through the reasons why, but we needed to be able to deal with networks with weighted nodes. There's a whole literature on weighted networks, and they normally mean there's a weight on the edge in the network. And that might represent the strength of a connection. If you imagine a trade network, for example, it might represent the amount of money that's shifted between two countries or two parties. You know, in the sort of brilliant capitalist elite example, for example, you might represent some things with weighted edges. There's also a reason sometimes to put the weight on the node, right? If you imagine wanting to weight entries in a trade network by GDP or by size of company or something, you might want to weight the node. When you're doing brain scans, you want to weight by the local density of brain cells and so on. So here we needed to do this for specific reasons, and then you need to calculate network metrics that are actually safe under this reweighting of the nodes. And that's a tricky thing to do. And we went down this rabbit hole of finding the literature on it and developing it. So there's a paper here which explains how to do node weighted measures for networks. We took the Python code that they had for this and we had to make it run a lot faster, and we had to parallelize it and so on. So if you want to do large network studies, or you want to do network studies where you think a weighted node might be useful, then please follow up with me, and there's a chance for some collaboration there, and we can share code and this kind of thing. So that's, I think, all I wanted to say. You know, we've done funky things with the Hadron Collider data, and we have some techniques which might be useful for humanities research somewhere.
That's fantastic. Thank you so much, Martin. That was a lot of information as well. That's really great. I really, I loved the common thread that I see between these presentations is that ability that network analysis can give us to capture, so that we can study it and share it, a incident or an event or an interaction that may be otherwise difficult to document, either because of the nature of the interaction, the ephemerality of what's been happening there, because of the difficulty of observing it, and then the research that can flow from being able to capture those things. I think that's fantastic, and I think that was really nicely, clearly put as a thread through those 3 presentations. So thank you very much for that. I just want to remind our participants, our attendees, that please feel free to pop any questions in the chat window, and I can post them to our presenters today. But I might kick off with the question. Many of the people who have attended today may be interested in applying this in their research, but also might be completely new to this environment, to this sort of analysis technique. Did anybody perhaps want to suggest what skills someone might need to start working in this space, and how they might get started in this kind of approach? It may be a question for Gareth and Jonathan more than for Martin, because I think it might have a slightly different approach with the large.
Use Python, get your hands dirty, roll your sleeves up. It's all on people's blogs. You can teach yourself.
Yeah, like Googling for tutorials is probably the #1 skill, like that kind of self-learning, self-initiative. Other people have done it and have shared how they've done it. I think the other thing I would say is actually it's not as difficult as it looks. A network data is pairs. It's just 2 columns in a spreadsheet. And if you're comfortable moving data between spreadsheets and plain text editors, that's an important kind of process to then get the data into formats that the various visualization packages can use. So that's definitely speaking to my experience in working with and kind of upskilling humanities, arts and humanities scholars.
What I would add to that is how important it is to reach out and look for people with expertise that can help you. I wouldn't have been able to do any of the things that I've done without significant help from people such as Alexis. I come from a humanities background. I don't have any mathematical training. I don't have any training in computers, but I do know what I want to achieve. And by talking to people who do have that expertise, I can learn what I have to learn, and they can tell me what I have to learn. But sometimes I can also get help, outsource some tasks that I can't do myself.
Thanks, Gareth. Our colleague Linda here has asked a question here. It's a question for Jonathan, complementing your visually attractive images. Could you share what visualization software you've been using?
So I use a mix. The ones that I shared today were produced in a software, like a network visualization software program developed in Europe. It's called Visone, V-I-S-O-N-E. I use it because it enables me to produce static images with a high degree of control over color and layout. And so the pathway to getting PDF or publication ready or presentation ready images is pretty straightforward in that program. It has some kind of network statistical analysis components, but really in my work, it's about trying to keep close to the sense of the event and the artist and to communicate that. And I would say I've been working with that program for 10 years, and so developed through trial and error my own, what I feel like is my own style to how to make things kind of legible to the people I'm communicating with. I've also used Gephi that Gareth has used, and that's also a good pathway in, and also produces good looking output. And the other thing I would say is to sort of try everything as it comes through, because these things are always in development, and there are always kind of new kids on the block. And I've most recently been using an online visualization package called Raw Graphs. And I did a whole exhibition just working with that. So, yeah.
Thank you so much. I know that there are online tutorials for the use of Gephi. That's reasonably easy to find, so that might be a starting point. But I have a question here from Lewis, who's talked about there's a rich area of mathematical and computational techniques to model networks like the ones you showed, which will help understand their properties and make predictions about how they might evolve, etc. Do you see any use for these sorts of theories in the work you showed? Or is visualization the main usefulness in the project that you showed?
Yes, I do. I do think we can learn from the past and apply knowledge to the future. I think that's a prospect. I'm very interested in working with visualizations of past performance data and asking questions with the cultural analysts and policy developers and the arts funding programs about kind of how our knowledge about, how the ecologies of performance making, how that could feed into future developments, future decision making. And I think the kind of modeling that you're describing there, Lewis, has application in that area.
My fantasy course would involve getting much more deeply into the mathematics, and would be open not just to historians, but also mathematics students and computer studies students. One of the things I find so exciting about this technology is its interdisciplinary potential. One of the problems with the way that the university is structured, and I think research in general is structured, is that so much of what is done takes place in little disciplinary boxes. Well, with this stuff, it's not just about getting outside the box, it's about forgetting the box and breaking into completely new territory.
So I completely agree, Gareth. And indeed, one of the things that we're doing, and Lewis was at a workshop that I was also at about a month ago. We have this program in applied data analytics, and I skipped over those slides in my talk. The idea for applying this stuff to Hadron Collider events originally came from preparing the social network analysis lecture in that course, and sort of getting inspiration from seeing this applied in lots of different contexts. And so we are designing courses which are indeed designed to be quite open. So I teach a general first year course that is a wide survey. I think it's just been opened up to humanities people, actually, And it's a wide survey of a whole bunch of different data science techniques where you don't need high-level maths or any programming. You just do simple gut-level understanding in Excel. So, I'd never use Excel to train a neural network by hand, but to teach a student, it's fantastic because you really understand what's going on at a very intuitive level. And the idea is if you do that course, you at least know the kinds of things you can apply and where they're useful. And then you can go on and we'll have other courses that are available where you can kind of upskill. But I think events like this are amazing. And I think that educational initiatives for everybody, for undergrads and PhD students and even postdocs to upskill will be amazing going forward. If there's one benefit to merging faculties, it has to be this, right?
I think that's we've had someone ask in the comments, can we please do that course? I absolutely agree with you, Martin, and Gareth and Jonathan, with all these observations. I think actually there's a real benefit in understanding how data works, aside from learning programming languages or particular visualization softwares, having that ability to sort of conceptually grasp what's going on is really, really useful. I'm really sorry for the people who've asked further questions in the chat window. There's always the difficulty with these sessions. Just as the questions get good, we run out of time. But thank you. I'm going to thank our speakers very much for their time. Encourage anybody who does have any follow-up questions about that, please reach out to me. And I thank our attendees for joining as well. It's been a really, really fascinating session, and I will share it on YouTube for anyone who wants to revisit later on. So thanks everyone for joining us today, and have a lovely afternoon.
Thank you very much.
Thanks everyone.
Thanks, Alexis. Bye-bye. Thank you, everyone. Bye-bye.